Please.
Yeah, for
E.
I took it to mean that when it said the expression computes a change in y,
Yeah.
I just assumed that if any small part of it you computed it,
But this is important too. How does it compute the change in y? If you were to take it that way, if you were to take, oh, a part of it does, how does it compute the change in y? By doing m times the change in x? No. Where do you see it computing the change in y? You say the top part. Is that rate of change times the change in x? No, it's final value of y minus initial value of y. It's not m times the change in x. M times the change in x is a product. That's computing the change in y as final value of y minus initial value of y. Yeah. Yes, sir? No, sorry. This is clearly the function we've been working on. This is our rate of change function. See that? You guys gotta focus on ideas, not trivialities. Like you gotta focus on. So maybe you have a point, but the real point is this is a function. Okay, so then why didn't you say it was? I'm not trying to trick you. I'm not trying to trick you. I'm not trying to trick you. Other questions? Yeah. For a very small, it's both. It depends on what h is. If h is not small, then it's approximate. If h is very small, then it's exact. It's both. It's both. Depends on h. Other questions? Yeah.
I got a little tripped up on C at first, reading based on function f.
Yeah.
I now understand that means that you're using function f in the function itself. But how would you say that? Like, what's the wording for that represents the function r? Like, what's the terminology there? Because that is the definition of function r.
Yeah. This is our rate of change function. Yes.
Okay.
This is our rate of change function. Yeah. Other questions?
Right.
Okay, so this is our focus right now, and this is answering this question is the understanding that we expect you to have about this. All these things are important regarding that, and that's the level and depth and breadth of understanding we'd expect you to have about this ratio, sometimes called the difference quotient. Sometimes that's called the difference quotient. Okay, last chance for questions on that. Okay. Where am I going? This one maybe? No. This one maybe? This one. Okay. All right, so here we go, where we're at. All right, I don't have my scribble pen. I actually have the pen, I just don't have the little cord that connects my pad to my laptop, so I can't write on the screen. So I did my best to make the PowerPoints complete, but I may have to roll the screen up and write a little bit on the board. That won't get captured in the video, so I have to replace that cord soon. Okay, where we're at. What's our endeavor? Given an exact accumulation, determine exact rate. Okay? More specifically, what do we want? We want closed form exact rate functions. What is that? Those are just familiar functions that are just a combination of basic operations and basic functions that you're familiar with. Sine, exponential, polynomials. Ones that you can just quickly plug in inputs, independent, and it'll give you lots of outputs, okay? So this is our goal, closed form exact rate functions. And what we've learned is every time we start with an accumulation function and get the closed form exact rate function, we just learned two things. We, of course, learned what the rate of change function was for that accumulation function, obviously. But then we also have a closed form for the accumulation function given that rate function. You see? So by getting a closed form rate function, it tells us two things. It also tells us now a closed form accumulation function given that rate. Okay, so we've been practicing that. Okay, so then approach number 2 is this rate of change function. This is the one you just took your quiz on. There it is. So this is the one we just talked about in the quiz, and we call that the rate of change of the function f with respect to its input or independent variable x. Okay? So this is where we're living right now. What? We know how much of something we have. We know the accumulated amount. That's f. And we want to know how fast it's changing. So this is how we build, how fast it's changing from the accumulation f. Okay? Given exact accumulation, function f, determine exact rate, function r of f. Okay? So we've found in these examples that with algebra and letting h get sufficiently small, this rate of change function can give a closed form exact rate function. Okay? And so now what we're going to do is we're going to start getting lots of these. And so we're going to build general rules to give us lots of closed form rate functions from closed form accumulation functions. Because the more of those that we get, then for every closed form rate function that we get a closed form accumulation function for that rate. Okay, but we're not going to lose sight of the meaning. So we're going to kind of summarize the meaning with one more example, and then we're going to go on to generating these general rules for getting closed form rate functions. Okay, and that very thing, the closed form rules of rate functions, is the very narrow part of the course which the mastery test is about. The mastery test is not mastery of everything we've done so far. It's mastery of a very specific, narrow part of the course, which is using these rules or these shortcuts to get closed form rate functions. Okay. So let's look at one more conceptual example. Make sure we have it. So here's this function g, and I'm showing a line through points 1, 4, and 4, 2 that are points on g. What's the approximate rate of change of g when x equals 1 according to this purple-pink linear piece pretending to be g? Go. What is the approximate rate of change when x equals 1 according to this linear piece of this linear thing pretending to be the accumulation function g? You could do it in your head. You could come up with an answer in your head. What is it? Negative 2/3. Negative 2/3. Okay, so that's going to be for h equals 3, the rate of change function for g evaluated at 1 is negative 2/3. Okay, how do we get a better approximation? Smaller h. Okay, so get a better approximation then. Here you go. Go. Now you're going to have to actually do something. Okay? Can't do this one in your head. Get a better approximation for the rate of change of the function g evaluated at x equals 1. I should have asked you before you did that, is this approximation going to be too large of a negative or too small of a negative? Too large of a negative rate of change or too small of a negative, or too small of a negative rate of change? Is the exact rate of change a bigger or smaller negative? Can you imagine through those 2 points or along that curve there, rate of change will be more negative. The exact rate of change should be more negative than this. What'd you get? Negative 1.311? Okay. Right, so the actual rate of change is more negative. For a change in x, there's more of a change in y, more of a negative change in y than that pink line shows, right? It's going down more. It's actually going down more than what that pink line shows. So this number shows that, right? That the actual rate of change, or closer to the actual rate of change, is a larger change in y for the same change in x. Okay? All right, and if we were to do, you don't do this just for time's sake, I know you can do it. So now this is helping you find what? A good estimate for the rate of change at x equals 4. And if you did the math, you would get this, negative 0.33. Okay? So what does the rate of change of g evaluated at x equals 4 equals negative 0.33 mean? What does it mean? Tell the person next to you, have we learned this yet? Go! What does that number mean? Saying that it's the rate of change is not explaining what the rate of change means. Okay? Yes, negative 0.33 is the rate of change of g at x equals 4. What does that mean? What does that mean? You guys, pair up. Right here. Talk. Everyone's talking to somebody. We never talked about slope. What does that mean? What does the number mean? Yes. The change in y is negative 0.33 times as much as a small change in x. What do you think? Given a small change in x near 4. Given a small change in x near 4, the change in y is negative 0.33 times as much as that whatever change in x you picked. That's what it means. If you didn't say that, you still haven't learned it. And we've been saying it for 6 weeks now. Okay? Now's the time to learn it. Given a small change in x near 4, y will change negative 0.33 times as much as that change in x. Today is the day. Okay? 6 weeks we've been talking about this. Okay? What the meaning of rate of change. Okay. So now this function g is actually, can I go on to the next screen? It'll be on the video. This function g is actually 12 over x plus 2. That's what this function is. Okay, so we want to find a closed form rate of change function. We want to find the rate of change of g with respect to x in closed form. Write down the first step to doing that. What's the first step that's going to allow us to figure out what the closed form is for the rate of change of g with respect to x? Everyone should be able to do it. How would we start that process? Okay, did you get it? The first step? Yeah. Uh-huh. So what's going to be what are we going to set up in order to work out what the closed form rate of change would be? Okay. And what would that be? Not sure. Okay, somebody, how about somebody new? Let's see. Did you get it right here in the green shirt? No? How about behind her in the red shirt? No? Who's doing their homework? Okay.
Just use the f of x plus h.
Okay, and what would it be?
So it would be 12 over x plus h plus 2 minus 12 over x plus 2 over h.
Right, we're going to write the rate of change function for this rule. It's this. You're going to write the rate of change function for this rule. How many people got it before I put it up? Good, good. Okay. So now we just have to do this. And it's not bad. We just need what? We're going to subtract in the numerator, so we need a common denominator. The common denominator will just be the product of the two denominators. Okay? So that first fraction, we're going to multiply top and bottom by x plus 2. The second fraction, we're going to multiply top and bottom by x plus h plus 2. And here's what we get.
Oh, that's awesome.
It's nothing, you guys. So I did two steps. I did what I just said, and then I also subtracted the fractions. So 12 times x plus 2 minus 12 times x plus h plus 2 all over the common denominator. All over h.
Is it x squared plus 2x
Oh.
plus 9?
What? What are you talking about? No, I don't think, no, that's not right. Okay, are we good on that? So now, what can we do? So we're just going to look at the numerator of the numerator. There's a fraction in the numerator here. We're going to look at that numerator, just expand and subtract. We're left with, all we get in the numerator when we're left is negative 12h. Do you see that? There's a 12x and a negative 12x. There's a 24 and a negative 24. And then all that's left is negative 2h. Negative 12h. That should be negative. That should be negative. I can't change it. I can't scribble. I'm in prison. Negative 12h. Oh, wait, maybe I can. Let's see. No, that's negative 12h. Make sure in your notes you got that. Okay? What now? H in the numerator, h in the denominator goes away. Negative 12. Should be negative 12. Okay, we're okay. Now we can let h be really, really small, like essentially 0. It's not going to screw us up anymore. And when h gets essentially really, really small, we just have 2x plus 2. 2 factors of x plus 2 in the denominator. No, you just write it as squared. Well, this is crazy. I could tell I did this fast. This negative should be up here. Just move that negative and just move it there. Okay? This should be negative 12 over x plus 2 to the positive 2 squared. Okay? Make sure. Negative 12 over x plus 2 squared, not negative 2. Okay, so remember, what did we calculate for small h? We calculated the rate of change at 1 was negative 1.311. I want you to find this value exactly now. Find the rate of change of g evaluated at x equals 1. Find an exact value. You can do it if you know what's going on. And you have the right rule. I don't know. Yeah, I have no idea. What'd you get? Yeah, what'd you get? Negative 1.33333333. Okay, that's what you should have gotten. Negative 1.33. Why? Close. What's the beauty of closed form? Just plug in 1, right? You just plug in 1, and it will give you this value rather than here's 1 point on the curve, here's another point really close. Find the change in y over the change in x. This is the beauty of closed form. Boom, you just put a 1 in, and it gives you that rate of change. Okay? Also, for 4, we got negative 0.33 when we did 4 using the individual points on the curve. we got a rate of change of, and an h of 0.05. Find an exact value for the rate of change of g at x equals 4. Find the exact value. And what'd you get? Negative 1/3, right? So both of them very close because our h was small. Make it just a couple orders of magnitude smaller and you're virtually exact, okay? So, but this, you don't have to worry about h anymore. You just plug in your value of x. It tells you what the exact rate of change is at that value of x. Okay, so see why we're so interested in wanting closed form rate of change functions. They make life really easy. It's really powerful. We can just, any x value that we want, boom, it just cranks out the rate of change for us. Okay, why? Because it was based on rate of change for a small value of h. Okay, questions on that? Okay, so now we're going to start. So all this is really looking at the marriage of the concepts with the algebra and kind of the computational side and how it's related to the conceptual side. So hopefully that's good. So because it's going to be focused in the next week or two, it's going to be highly focused on computation and algebra. We don't want to lose sight of our understanding here. Okay? All right, so let's talk about some categories of functions and what the rate of change will be. So the first one we're going to look at is constant functions. An accumulation function f never accumulates any changes in its value. It's the amount stays constant. So the accumulation it's never accumulating any changes. What's the rate of change? 0, right? So there's 0 change for any change in x. There's 0 change in your accumulation. So let's see that. Let's see how that plays out with the math. Okay? So show it mathematically. So if your function f is a constant c, I want you to use, what does this function say? What does the rule tell you to do to get the corresponding value of the dependent variable? So you've got some value of the independent variable. What does this function tell you to do to get the corresponding value of the dependent variable? What does it tell you to do? So easy, it's hard. What does it tell you to do? Yeah. No. Yeah, what does it tell you? Set it equal to c. So when x is 5, what is the value of the dependent variable? C. When x is 10. C. When x is negative 2. C. No matter what value you have for your independent variable, this function says value of the dependent variable is c. Okay, now so we're going to use the rate of change function for f to show that the rate of change is 0. Can you do it? So use our rate of change function for f to show that the rate of change of f with respect to x is 0. Can you do it? So I suggest starting by writing down the rate of change function for f. Start by writing down the rate of change function for f. Who can tell me what the rate of change function for f is? Right here, purple shirt. What's the rate of change function for f? No, what? In general, for any function f. I know Joseph knows. How about right here? What's the rate of change function for f? Yeah, for any function f. You got it. F of x plus h minus f of x over h. What is f of x plus h? C. What is f of x? C. What's c minus c?
0.
Doesn't matter what you put in for your independent variable. this function says it's always c. And so therefore you get c minus c over h, 0. And that's what we said. We said that if the function's accumulating no changes, it's a constant function, its rate of change should be 0. And so it works. Good? Yay. All right. Okay, soon that's the first. Just constant functions. The rate of change function is 0. Okay? What about a constant multiple? So a constant multiple is when you have a constant times another function. A constant times another function. Here's an example. At every moment in time, John has traveled 5 times as far as Mary. What can we conclude about John's speed relative to Mary's speed? 5 times as fast, right? Okay. So if f of x is John's total distance after x hours and g of x is Mary's total distance after x hours, then this says what? That the distance John travels is always 5 times the distance Mary has traveled. So what's the rate of change of f with respect to x then? What's the rate of change of f with respect to x, or John's speed? It's always 5 times, not greater, 5 times Mary's speed. How would we write that? The rate of change of f with respect to x is 5 times the rate of change of g with respect to x. Okay? So if you have a constant times a function, this is an example of how if you have a constant times a accumulation function, you want the rate of change. The rate of change function is 5 times the rate of change of that function that it was multiplied by. Okay? So generally, so we're going to read this as the rate of change of f with respect to x is 5 times the rate of change of g with respect to x. Okay, so in general, this is just now. So if c is a constant, all you really need is this. Don't you hear all that? But if you have a function that's a constant multiple of another function, function f is c times, or the values of the dependent variable of f are c times values of the dependent variable of g, then the rate of change of f is always c times the rate of change of g. So this is, sometimes students get these two mixed up. If you just have a constant by itself, the rate of change is 0. But if you have a constant multiplied times a function, the rate of change is that constant. It does not 0. You just hold on to that constant, and it's that many times. The rate of change is that same constant times the rate of change of that original accumulation function, in this case g. Okay? So don't get those two mixed up. Make sure you know what situation you have, okay? All right. Okay, so let's do this. We can do it. 9 minutes. Here we go. So here we go. This is functions of the form x to the n. Functions of the form x to the n. So this is basically a monomial. X to any power. X to any power is what we're talking about. So just in order to do this, we're going to need to talk about the binomial theorem. Okay, the binomial theorem says we know x plus h squared, when you FOIL it out, you get 3 terms, right? And x plus h cubed, when you multiply it out, you actually get 4 terms. So what about x plus h to the, that's x plus h to the 4th? And so this pattern starts to emerge with higher and higher powers of x until you get x plus h to the n. It always starts with x to the n. See that? And then what? Then the power of x goes down by 1 each term, and the power of n goes up by 1 each term until you have h to the n as your last term. Okay, and then there's a bunch of coefficients. We don't need to talk about the coefficients, but the coefficients, there's a formula for those coefficients. We don't have to worry about that. But the general, we know there's x to the n at first, h to the n at the end, and then as you go term by term, the power of x goes down by 1, power of h goes up by 1, okay, for each term. All right, so we're going to need that formula to find the rate of change function for f when it's of the form x to the n. Okay, ready? So we start with our rate of change function. Okay? If you haven't memorized this yet, memorize it. This is where we're going to live, okay? We're going to start making these rules by always starting with the rate of change function. So what is f of x plus h? That's the thing we just looked at. It's going to be x plus h to the n. And then f of x is going to be x to the n over h. Right? We all could do that, right? Piece of cake. So that x plus h to the n is what we just talked about on the previous screen. So we're going to put that in there. And then notice, minus x to the n. So what do you notice? We're going to take that thing we did before and then subtract x to the n. What happens? You see that they go away, right? You got a positive x to the n, the first term, minus x to the n here. Those are 0. So we're left with all this from the second term to the last term of x plus h to the n. So those go away. Now, what do you notice about every one of these terms? They have an h in them. So now that we've got rid of the x to the n, all the rest of the terms had an h. And we can factor, just like we've done in previous problems, we can factor out an h. And we know that will be 1 with the h in the denominator. So we're going to factor out h. And now h over h is 1. And so now we're just left with this. Okay? And what do we do now? We want exact rate of change.
So you can, all the h's that you have on there, as they're going to 0, you cross them out.
Right. We're going to let h be exceedingly small. And so then anything with an h in it will be essentially 0. And so our exact rate of change function is, so those all have h's. Exact rate of change function is n x to the n minus 1. For exceptionally small values of h. Oh, time to spare. Okay, cool. So you don't, you can watch the video again. What I emphasized and what I said is all you really need in this. So there's a lot of details in the middle here that look really scary. But when I explained it, when I talked it through, that's what you need to recognize and understand. All these, all these crazy exponents and coefficients, in the end, they don't really mean much for what we want to do. So if you watch the video again, just really focus on what I emphasized, okay? Where I drew your attention to, because that's all you need, and it's not hard. It's not, what I was speaking of is not hard to see, okay? So this, then, if f of x equals x to the n, the exact rate of change function is n x to the n minus 1. Or the rate of change function of x equals n x to n minus 1. That's our exact rate of change function. Okay, and that's for h. It's exact because we said h was really, really small, and that's what gave us that result. Okay, so we have 3 general categories of functions. Constant functions, rate of change is 0. A constant times a function, to get the rate of change of that, you do constant times the rate of change of that function. Okay? And then now if you have a function that's of the form x to the n, the rate of change function is? And so as a visual thing, students think of taking the n and moving it down in front and then reducing the exponent by 1. So if it's x to the 5th, if our accumulation function is x to the 5th, then the rate of change function is 5x to the 4th. 5x. If it's x to the negative 3, negative 3, x to the negative 4. You'd still subtract 1. So when they're negative, they become a bigger negative. Okay? Negative 3x to the negative 4. Okay, so I want you to... So this is called the power rule. Okay? This third one is the power rule. Okay, one more. So this is a function that's a sum of other functions. What are we interested in? We're interested in the rate of change of k with respect to x. We're interested in the rate of, so I'm going to write on the board here. Screens. So I want you to write out the rate of change function in general for the function k. Write out the rate of change function in general for the function k. Go. That's the first step, always. We want to know the rate of change for k, then you're going to write out the general form of the rate of change with respect of k with respect to x. Let's see. How about this one? You got it? Tell me. No, for k. For k. K of x plus h. So the rate of change of k with respect to x is k of x plus h. Keep going. Minus k of x all over h. That's your first step. This is what we're interested in. We're interested in the rate of change of k with respect to x. Now, what is k of x plus h? It's f of x plus h plus g of x plus h. What's k of x? F of x plus g of x all over h. So what are we going to do? So I'm going to regroup. I'm going to regroup f of x and minus f of x plus h. I'm going to group those together. And what will that be? When I group those together over h, what will that be? And what will that be? That's the rate of change of f. And then I'm going to group these together. The red ones. And when I group those together and put them over h, what am I going to get? The rate of change of g with respect to h. So it's like backwards now. You have to recognize that when you have that ratio, that's the rate of change of f with respect to x. And then the red one, that's the rate of change of g with respect to x. So skipping a step there, what is it equal to? Rate of change of f with respect to x plus. So it's exactly what we would hope for. If you have a sum of functions to get the rate of change, what? It's the sum of the rates of change. This is great, right? This is exactly what we would hope for. It's the easiest thing possible. If your function is a sum of functions, then to get the rate of change of that, you're going to take the rate of change of the first and add it to the rate of change of the second.